In the last video, we talked about the hypothesis representation for logistic regression. What I'd like to do now is tell you about something called the decision boundary, and this will give us a better sense of what the logistic regression's hypothesis function is computing. To recap, this is what we wrote out last time, where we said that the hypothesis is represented as h of x equals g of theta transpose x, where g is this function called the sigmoid function, which looks like this. So it slowly increases from 0 to 1, asymptoting at 1. What I want to do now is try to understand better when this hypothesis will make predictions that y is equal to 1 versus when it might make predictions that y is equal to 0, and understand better what the hypothesis function looks like, particularly when we have more than one feature. Concretely, this hypothesis is outputting estimates of the probability that y is equal to 1, given x and parameterized by theta. So if we wanted to predict is y equal to 1 or is y equal to 0, here's something we might do. Whenever the hypothesis outputs that the probability of y being 1 is greater than or equal to 0.5, so this means that if it's more likely to be y equals 1 than y equals 0, then let's predict y equals 1. And otherwise, if the estimated probability of y being equal to 1 is less than 0.5, then let's predict y equals 0. And I chose a greater than or equal to here and a less than here. If h of x is equal to 0.5 exactly, then we could predict positive or negative, but I put a greater than or equal to 2 here, so we default maybe to predicting positive if h of x is 0.5, but that's a detail that really doesn't matter that much. What I want to do is understand better when is it exactly that h of x will be greater than or equal to 0.5, so that we'll end up predicting y is equal to 1. If we look at this plot of the sigmoid function, we'll notice that the sigmoid function, g of z, is greater than or equal to 0.5 whenever z is greater than or equal to 0. So it's in this half of the figure that g takes on values that are 0.5 and higher, right? Because this notch here, that's the 0.5. And so when z is positive, g of z, the sigmoid function, is greater than or equal to 0.5. Since the hypothesis for logistic regression is h of x equals g of theta transpose x, this is therefore going to be greater than or equal to 0.5 whenever theta transpose x is greater than or equal to 0. So what we've shown, right, because here theta transpose x takes the row of z. So what we've shown is that our hypothesis is going to predict y equals 1 whenever theta transpose x is greater than or equal to 0. Let's now consider the other case of when our hypothesis will predict y is equal to 0. Well, by a similar argument, h of x is going to be less than 0.5 whenever g of z is less than 0.5, because the range of values of z that cause g of z to take on values less than 0.5, well, that's when z is negative. So when g of z is less than 0.5, our hypothesis will predict that y is equal to 0. And by a similar argument to what we had earlier, h of x is equal to g of theta transpose x, and so we'll predict y equals 0 whenever this quantity theta transpose x is less than 0. To summarize what we just worked out, we saw that if we decide to predict whether y is equal to 1 or y is equal to 0, depending on whether the estimated probability is greater than or equal to 0.5 or whether it's less than 0.5, then that's the same as saying that we'll predict y equals 1 whenever theta transpose x is greater than or equal to 0, and we'll predict y is equal to 0 whenever theta transpose x is less than 0. Let's use this to better understand how the hypothesis of logistic regression makes its predictions. Now, let's suppose we have a training set like that shown on this slide. And suppose our hypothesis is h of x equals g of theta 0 plus theta 1 x1 plus theta 2 x2. We haven't talked yet about how to fit the parameters of this model. We'll talk about that in the next video. But suppose